Well, I guess it is start time. Actually, a little past start time. And I keep telling myself I'm going to fix that new computer with the icons display so I don't run into the problem, but I guess I got to deal with it one more day. I forgot to do that. I thought I'd get started by just a little bit of housekeeping here, getting us started, starting with this very simple question. What's happening the next time we meet? Haha, test, right, good. So you haven't forgotten. So just in case you did forget or needed to be reminded, next Tuesday is a test here. So as you know, we finished up the mechanical waves. If you were looking at the syllabus, we're ready to start the next section, which is on some thermodynamics. And so more on that in just a second, but that's where we're going here today. I thought I'd also take maybe a moment to show you a little bit more about waves before we put complete closure to it. But I just want to emphasize, next Tuesday, test, all right? And it's, you might want to call it a quiz. Remember, it's not the standard 5. It's only the 3, all right? I suppose that's the good side. Bad side with that is it's also only an hour, too. So we've got that first hour. So what we'll do is we're going to take the test on the first hour. And then after that, then we'll continue on where we leave off today, which is this chapter 19. So, you know, the test will be from 5 to 9 to 10, and then from 10 or, you know, a few minutes after 10, whatever it takes to change gears there, we will continue to lecture. So again, that's different than the normal. Also, maybe a little different than the normal, although if you had 122 last semester, you're aware of this. But I want to mention that over in the lab, or this lab here, the PS116, we'll open that. And so Don will be over there ministering the test. So if you prefer to take the test over there, I encourage some to go over there. The whole idea is give us a little bit of spreading out room. We are very tight in here, and as you can see, if everybody's here, there's places where people have to sit without a desk, and that doesn't make a good test taking here. So by opening that, we can get, you know, well, I think there's like 18 tables there, and if there's only one person at a table, that's a lot of room, and 18 people less in here. That alone is helpful, but you could even double up people in there. I don't think you guys over there, you ever double up or no? Sometimes? Okay. And then, of course, those of you on the DSPS, we got that DSPS room, so you meet me at 8 o'clock at the DSPS room, and then, you know, we'll, and so some of you will be over there. So the rest of you will be here with me, some of you will be with Don, some of you will be over in our DSPS room. Yeah.
Do we still get the full time for a half test?
You get 1 hour.
Okay.
Yeah. Yeah, so you get, or 1 hour, 5 minutes, how's that? You get the 5 to 9 till 10, okay? And, again, if you, and I'm going to use that as the lead-in then for the review. Some of you, I've already noticed, you've already been working with Don's review and seeing the test questions, and he's got a bunch of them. But he mentioned this, and he wanted me to mention two things. First one being the review for Sunday. So Sunday, even though it's the holiday weekend here, Friday, tomorrow I guess, and then Monday is a holiday, Don wanted to make sure you guys had a chance here on Sunday, so 1 to 4 will be his review, and he'll pass out those practice tests as he normally does if you guys hadn't already picked it up. The other thing is that I think will be very helpful, also given that the test is coming up, and even though tomorrow is a holiday, so the campus will be closed and nobody will be around probably except you and Don here at 1 o'clock. So Don goes, you know what, maybe we should just do that MC class anyways, because it's right before the test, and even though it's a holiday. And we're going to trade that off, actually, coming up. And so this is kind of the warning. We're going to swap it out. There's a Friday coming up. Let me think of the date that we're going to have to cancel the MC. And it's not, you know, right before a test, so it makes a lot of sense to do this one. March 1st. And so I don't know if you want to make a note of that, but March 1st there will be no MC. That room will be occupied all day and closed up and locked off to students, and I won't go into detail of all what it's used for, but we need to cancel that class, and that room's for a special program that day here. And so, and Don will be tied up in that as we are doing interviews and stuff. So anyways, there's that no MC on the March first. Anyways, but there is one tomorrow. So anyways, if you're around working on those, I encourage you to go Friday, encourage you to go Sunday, encourage you to come out here Tuesday and just blow away the test and have the first test under your belt with a strong grade and going into the thermodynamics here. All right. So that's the housekeeping I said I wanted to do. Other than that, I'll get started here a minute in the thermodynamics, but I thought before I actually even led into the thermodynamics, I'd show you one other thing that I really wanted to show you, but I was also trying to do a whole chapter each day, these last 3 ones, and it was just, too much. So I go, I'm just going to pause a minute and show you these standing waves again in a sound tube. Partly because I didn't get a chance to show you what we call a Rubens tube, and I want you to see that. It's kind of neat. The other reason is because the silly one I had last time was cracked and didn't work, and I felt cheated, and I'm thinking you might have felt cheated, like, oh, it didn't work. So I thought I'd bring another one. This one's a little beat up, that's why I didn't grab this one, but at least a half hour ago it worked great. So we'll see. I even brought a backup too this time. I go, I'm bringing 2 just in case this one doesn't seem to work. But I'll just remind you of hopefully the obvious. I brought the wave machine out here one more time. If I were to make some movement down this tube, there would be vibrations, right? And they would go to the end of the tube. And at the end of the tube, they would reflect back. And they would go back and forth. And so this was our second scenario that we spent the most time. 2 waves traveling in opposite directions. They would develop a standing wave pattern. And of course there are different patterns. This one, notice, has an antinode here where my hand is moving, an antinode on the end. That's the open tubes. Other places inside, of course, do have antinodes here, an antinode there, an antinode there. So there's 3 within the tube and 2 on the end. And and then from that we calculated then how long the wavelength is. Also said, of course, that's not the only pattern. That is one pattern, but there's an infinite number of patterns, right? And so I'll let this thing stable out and maybe show a different pattern. Maybe one at a higher frequency. Maybe one that looks like this. Whoops. Right? And so there would be a shorter wavelength or higher frequency. Again, the endpoints would be nodes. And so many of these are possible. And that's what the sound tube was supposed to have you pick up with the ears. If I spin it gently, there's one tone. If I spin it a little bit faster, there's a different one. Faster, faster, faster. Right? And so each of those patterns can be separated out based upon how fast the air is going out, and that's what this sound tube is all about. Like I said, I think more interesting than last time. But the Rubens tube, this is a neat one, because I can turn this on and send the sound waves down. And before class started, I was out here playing with it, and one of the patterns is at 1,000 hertz. I'll turn it off here, but this looks exactly like the equipment you use this week, although I guess a third of you still have the lab to do today. But we got a speaker on one end, we send the waves down, and in this case it bounces off a little plunger here and comes back. So inside of this tube we have a set of standing waves, right? And so like this pattern up here, even though I can't see the molecules moving, they would be moving back and forth, right? There would be places that they're moving very fast, antinodes, and places where they're barely moving. Fair enough? And what makes it a little more interesting to see here is, what if I have this tube filled with gas? There's small holes in the top of this tube, and so as the gas comes out, we have a flame. If we turn off the lights, we can see the flames a little bit better. Let's see, that might be a little high. I'll try that one first. What happens if I turn on the sound? Oops, looks like a couple of them went out. Uh-oh. All right, take a guess. What's going to happen when I turn this on?
I'm assuming that some half of the candles get blown out because
And let me. But if I find just the right frequency, or sets of frequency, maybe I'll leave it at that one, is you can better, I think, better visually see. It looks like some of these tubes are either plugging up or the gas doesn't want to come out. Maybe I'll turn it down a little bit because I don't know which is better to see. But as you... bummer. Some of them aren't getting the gas to come out. So maybe I better quickly go through this. There's another one. Another one. Another one. And I told myself I wouldn't spend too much time here, so we better get started with our thermodynamics. But there is a nice one. If, I don't know what happened to these holes. How come the gas isn't coming out anymore?
Maybe they're shot.
Yeah, maybe I'll, if I turn it up, maybe will more gas out? Yeah. So a few, other than the fact that a few of them seem to get plugged, I'm hoping you can see what looks like what I was doing with that machine over there, where you can see the different patterns, and they're for the motion. There's one. There's kind of another one.
So where there's an antinode in the flame, the air is more compressed inside the tube there?
Well, yeah. Okay, good. You said it right. Yeah. Yes, that's exactly right. Yes. And because it does get a little phase shifted, because remember, you can think of the sound waves based on the pressure, or you can think of the sound waves based on the motion. But your comment about the pressure is right here, and so you could see, I think, the pattern, like I said, visually with the flame, as you can see the pattern here with the motion of the rods.
So wait, antidotes are where the flames are, and those are where the little flames are, or is it the other way around?
Well, we go back to, are you talking about the displacement wave, or are you talking about the pressure wave? So, okay, the pressure wave, then where it's really high is where the pressure is high, right? And so that's the antinode. Okay, and which is a phase shift from between the displacement wave. Okay. All right, well, anyways, with all that said, I know you guys have been working on that and working well, so I would encourage you to keep working. I'm going to use this day to start us forward then into our thermodynamics. And so now we go on to the next unit. As I said at the beginning of this class, it's worth saying it again, is we have 4 major units. It's not like our Physics 121 or 122. In 121 we start with mechanics and we do all mechanics, and it just gets harder and longer and more advanced as we go along. 122, same thing with our E&M. We start with electricity, from that leads to magnetism, so that leads to electricity and magnetism, and it just grows and grows and grows and grows. This area here is kind of 4 separate pieces that we start with waves, and then we kind of stop. And you can see there's a lot more to waves. In fact, you probably can see there's a lot more to mechanics and E&M, but we got to stop at some point, and it's just not a whole semester's worth of studying. And so later on in your education, some, probably not all, will go and study mechanical waves in one way or another. And then this unit begins here. So we start here very simple. That's kind of the good thing, is we got a new clean slate here. You're going to see right here in this chapter, we start with a lot of terminology, a lot of words, probably a lot of stuff you're already familiar with, like what's temperature, what's pressure, what's kinetic energy, okay? And so that's why it is a good place to get started, especially since I know your focus right now is not so much on the thermodynamics, but on the mechanical wave that the test is coming up to. So I'll just take these 2 hours to go through to kind of go through this first chapter and bring everybody up to the same level where you may or may not been exposed to what's the definition of temperature, what's the definition of thermal equilibrium, what is thermal expansion, and we got a few setups here for thermal expansion. In fact, I'll even take this opportunity to remove these waves from up here. Better postpone. Looks like the computer's trying to restart there. All right, so I will, as I said, kind of get started here and say, all right, what are we about to do? Well, chapters 19 through 22 is our next big step, our next big unit. The title, as I just mentioned here, is our thermodynamics. And kind of in a layman's term, what would be thermodynamics might be this. It is this relationship between heat, temperature, pressure, density, work, and I'll stop, energy, ... Right? And so we're going to be looking on here and saying, all right, let's really kind of extend really all of our mechanics. We are going to look at, like I said, thermodynamics. What happens when you take something hot and put it next to something cold? What happens if you take some gasoline and you put it in the cylinder of an engine and you burn it and it explodes? What does it do? And it has forces and pushes on pistons and makes work, and how much work? And so these are the steps we're going to do in these next 4 chapters. This first chapter, as to be expected, is that introduction chapter. You know, what is thermodynamics? What is temperature? What is thermal equilibrium? What is happening on a molecular level? And so the title of this chapter is temperature. And the goal here is to get you to understand a little bit more about temperature. And then the consequences of objects at different temperature. And so I'm going to put this on the board here and kind of explain my approach to this. I would say there's often 2 levels of looking at our thermodynamics. The first level is what I would call a macroscopic view. That is the big picture, looking at it from a point of view bigger than the atom, much bigger than the atom. Really, kind of the things that we're going to be talking about the most are really at the macroscopic level. I burn a flame. I have a hot piece of metal that I put in cold water. I have a big container of gasoline that I then burn in a cylinder. I mean, these are these big pictures. And we can talk about things like temperature without ever going down to the lower level, the microscopic scale. And this would be saying, look at what's going on down at the atomic level. This is what we're going to call the kinetic theory. And I'm going to make a wild guess, assumption. And I think it's true. I'd be surprised if it wasn't true. I bet every single one of you know that all materials, including, so I have a little block of aluminum or anything? Well, including this little brass one. If you were to get down to a microscopic level, what would you see? Atoms, right? Lots and lots of atoms. And here's why I say that, because I think your author makes a little bit too much effort of staying away from the microscopic level at the beginning. And I'm going to just start off and start incorporating the microscopic level at the beginning. And he kind of just avoids that here at the beginning and says, he's pretending like you are the early scientists of 1700 and you don't know that these things are made out of atoms. Now the good part about that is he wants to make it clear, and I want to make it clear, is that we can talk about things like temperature without ever saying anything about the motion of the molecules, right? We can put a thermometer in there and say the temperature is. We can talk about pressure without saying where does the pressure come from, right? In fact, probably a good place to get started to illustrate that is right here. What would happen if I were to take a hot object and put it next to a cold object? Well, again, you probably already know this before we got started today. What do you think is going to happen to just say the hot object? It's going to cool down. And what do you think is going to happen to the cold object? It's going to warm up. And what we like to say on a first level, on a macroscopic level, is we say there is a transfer of something. Something moved from one to another. And so our first word is heat. That's what moved. Something called heat, the quantity heat. Now I want to take this one step further. Even though your author won't quite do this until a few chapters from now, he'll say, let's look at the microscopic level. What is the difference between something hot and something cold? It's the speed of those molecules. So I'm going to, like I said, jump a little bit ahead of your author here and show you this. Here, it's supposed to be our representation of what would be happening on the microscopic level. I'll turn it off because it's kind of noisy. But on the microscopic level, those BBs bouncing around there are supposed to be atoms. And that might represent the cold one. And so these BBs are moving kind of slow. But again, looking at a microscopic level, what would be something that is hot? Yeah, okay, so there's cold. What's hot? There's hot. There's cold. There's really cold. Yeah, that is what's going to become our absolute zero, which I don't think he'll use that word yet. He doesn't use it for a while here, because again, he's staying away from the microscopic view. But as I'm going to say here is, I'm going to start incorporating it just a little bit, not too much. I don't want to get too off of the flow of the book. I never think that's a good idea for a lecturer to get off the flow of the book or use different symbols. That just really fouls up the students. Like, well, okay, what was important? Where am I going here? But I do think he should, and that's what I'm going to do is take a little time. I'm not going to wait all the way. He waits till about the end of chapter 20 before he starts talking about the molecular motion. See, because I think that's kind of important to put right here. If I have a visual picture, what would I say about these molecules next to the hot one? They're moving a little bit faster, right? What about these ones that are cold? A little slower. And in my mind then, the heat makes a lot more sense to me if I think of this as, here is a fast-moving molecule next to a slow one. What do you think is going to happen when these two bump into each other?
The fast one bumps into the slow one.
Yeah, this fast one hits the slow one, making the slow one go faster, and also at the same time making the fast one go slower. Exactly. And so what really is heat then makes a lot more sense than just calling it heat. Heat then really is an energy. And that's really what I want you to get here at this beginning part. This word heat is just another word for another type of energy. And that hopefully it's not a surprise, because we did that in our mechanics, right? We took two objects, we collided them together, we did conservation of momentum, and we looked at how much kinetic energy. We saw the kinetic energy had lowered, and we said, where did it go? Into heat during the collision of two carts coming together, or two cars coming together. And then we said, and I don't even know if we went that far in class, but if we were to look at the microscopic level, we would say, well, that motion is the kinetic motion of those molecules during that collision. And so what we have is a form of energy. So heat is a form of energy. It is a form of kinetic energy. It was a form of a microscopic kinetic energy. Now, I shouldn't spend too long here because I don't want to really spend right this early on talking about the microscopic level. We will do a lot more of that, but I do want to make sure you understand the macroscopic, and I think you can understand the macroscopic a little bit better than just don't call it heat. I mean, understand why it's a heat and why it's a transfer. It is a kinetic energy of the molecules themselves.
Yeah, I was going to say, why do they separate the kinetic energies into heat and macroscopic kinetic energies?
Well, they have a lot of different, I mean, their behavior is different because the heat energy is a random kinetic energy. I can't really control it. I don't know where it's going. And that's not the discussion you want to have with a car. A car, you want the kinetic energy. You want to, make the car go to the left or to the right. And so you want all the molecules going in the same direction in that case. Whereas when the car just sits there and gets hot, then some of the molecules go that way, some of them go that way, some of them go that way, and the center mass of the car doesn't move, even though it has more kinetic energy. So really, so that's why, so is what we often call the kinetic energy we learned in mechanics is the bulk kinetic energy. What's the kinetic energy of the center of mass? Yeah. Well, anyways, like I said, that is just kind of a long way of hopefully telling you the obvious that heat is an energy. In fact, I'll go one step further to make sure that you caught this. This is the energy that is exchanged between the objects. So let's just say, for example, these two objects were at the same temperature, and I put them together. Would there be any heat between them?
There will be, actually. It's transferring, but it's transferring equally in both directions.
Okay, so there's two subtleties I want you to see. This is really the net exchange. And then so the two molecules hit each other, there will be a chance where one's going faster and one's going slower. You're right. Now, I don't want to spend too much time on that yet because, again, that's too much focus on the microscopic level. But I do want to make sure you saw the other important thing. Heat is the energy exchanged between them. If these two objects were at the same temperature, aren't the molecules moving around? Isn't there a lot of energy stored in here because the molecules are moving? And isn't there a lot of energy stored in this one because the molecules are moving? And so when I say zero heat, I am not saying they have zero total energy. Did you catch that? Heat is not a word that we use for the total energy of these molecules. Heat is a word we use for the amount of energy that is exchanged. Fair enough? If I have $100 and you have $100 and we don't share, we're not broke. We each have $100, but our exchange is zero, right? If I give you 10, then our heat is the 10. The amount I have is now 90. And so don't mix those. Question.
Is it possible for a single atom to have the temperature? How would that?
Not really. Not really. Let me define temperature and then maybe I can address that. But temperature is defined as the average of all the energy of all the molecules. And so if you have just one, you really don't have a good definition of temperature. All you have is kinetic energy of one molecule.
Could it vibrate by itself without running into other atoms?
Well, it could ricochet off and you could focus on just that one. But if you focused on that one and you called its temperature related to its energy, what will end up happening is it hits one, maybe that one was coming in and now it goes real fast. And then it hits another one that was moving away, so now it goes slow.
I didn't mean take the temperature of one atom. I mean if an atom was by itself, if it was isolated.
But it wouldn't vibrate if it was by itself, it would just move.
So it wouldn't have any temperature.
Right, unless you wanted to relate it. And we do this sometimes, but it's not really a good idea, depending what you're doing, just to relate how fast it is it's moving. That's why defining temperature in the upper edges of the atmosphere is very difficult, because these atoms are just whizzing by really quick. And you look at that and you go, wow. And if you base it on temperature, you end up saying the temperature at the surface of the atmosphere is incredibly high. Really? And you put something up there and it freezes. It freezes because seldom does anything hit it. There's so few of them. So statistical average is when temperature is well defined. Yeah. In fact, my good roommate in graduate school was. That's what he did his whole PhD thesis on, was the movement of 20 sodium atoms. And it was always fun talking about the difficulties they have defining temperature, and just kind of stayed away from it because you don't have a good statistical average on 20 versus 20 billion. Yeah. Okay, so I hope you caught that. And again, maybe I already spent way too much time on the microscopic level, but at this first level, here's what I would say. I would say when you put those two things together, energy moves from one to another. I'm going to call that heat. That's the main point I wanted to say. That's the word heat. Energy flows from one to another. Which brings up this question then. All right, now that we got our new word for today, our new quantity, what are the units to measure heat? Joules, of course. Good, right? Because joules is, our heat is an energy. So if you caught the idea that it is an energy, then you caught the idea it is joules, unfortunately. The early scientists did not know it was an energy. They thought it was a whole nother quantity. Kind of like, water would move from point A to point B. There was an actual flow. So they gave a whole different set of units to measure this new quantity. And I think you guys know it. I heard you some say, what's the other unit?
Calorie.
Yeah, a calorie. And so we are going to use calories also for our energy. Now, since these two both measure energy, there must be a connection to them. It was Joule who eventually made that connection. He was the brilliant one who said, heat is a form of energy, and I'll prove it to you. And your book talks about the little experiment he does where he took a weight and he hangs it up in the top of his laboratory room with it potential energy, and he knew how much it had. And then he let that weight come down, and in the process it went through a pulley, and he had like a beaker of water here, and it had some stirring paddles in there. And then he put the thermometer in there, and so as we lost potential energy, he measured the water warming up. Because what is the definition of a calorie? Okay, so it is, I'll just put number of energy, the amount of energy needed to raise 1 gram of water 1 degree Celsius. So again, that was what the early scientists did, because again, they thought of it as this fluid, this quantity, separate from energy. So they needed a separate unit from energy, and they needed a way to do it. And they did all their little experiments with water, and it made sense then to talk about, okay, however much has to flow into 1 gram of water to warm it up 1 degree, that is what we will call a calorie. And so in Joule's little proof experiment, he just took that heavy weight, he let it fall, and he saw the water warm up, telling him, look, that is my proof that that potential energy now became heat energy. And then he measures it. It's very easy to calculate potential energy, MGH. It's very easy to calculate calories if you put a thermometer in there. And between those two, he comes up with 4.18 joules is then equal to 1 calorie.
How did you get the water to heat up?
He just put a paddle wheel in it and it'll spin.
And it spun because of...
Oh, and it's, yeah, so the paddle wheel, the paddle wheel will be hooked to a rope that is hooked to a cable that is hooked to the weight. And so as the weight goes down, it turns the wheel. Okay. And I think it wasn't just one wheel, otherwise it tends the whole fluid, but he had layers of wheels. One went clockwise, one went counterclockwise, so that you didn't turn all of the energy just into rotational energy in the liquid, but you let it eventually come into heat energy, and so the water wasn't moving. And what's the temperature? And like I said, this is what he came up with. So that was his famous experiment of how showing heat is an energy, and not the only one. He noticed it during the Industrial Revolution. He was, I guess he was an industrialist and was part of the manufacturing process of cannons for the British Navy. And they had sharp bits at the beginning, and they could bore the cannons really well, and then they got dull, and what ended up happening is it didn't bore, but the metal got really hot. And he noticed that and said, our machines are working really hard, and they're not cutting the material, but now they're getting hot. And so he kind of started putting all those together there. Anyways, so like I said, I think a lot of this you already know. If not, that's why I said this is why this is the introduction chapter to, what is heat? What are the units to measure it? And so we've got 2. All right, fair enough. There's another word I kind of alluded to. I didn't use it here, but this was what I was saying about the total energy. If we want to talk about the total energy that is inside of that block, we will call that its thermal energy. So again, let me just say it one more time here. The word heat we reserve for a special case. Although I got to admit, sometimes we get careless and call the total energy, how much heat does the object have? But the truth is, the heat is, I'll say it again, what's the formal word for the heat? How much energy is exchanged from one to another. But what I would call then the thermal energy of the object is what the total energy would have. That is, if I took the energy of one atom plus another, plus another, plus another, plus another, again, maybe going to this lower microscopic level, but if I look at every little atom, I would then add that up and say, that is the total energy it has. And so something could have a lot of energy just because it has a lot of molecules. It could be cold. I mean, does the Arctic Ocean have a lot of energy?
Yes. Depends what you call a rock.
Okay, I would say yes, it does. Not because the Arctic Ocean is warm, but because it's big. There's lots and lots and lots of them. Okay? And that's important as we get the difference between the thermal energy and the temperature, as we will talk about here in just a second. So it's total energy. Now, I should also probably be a little more careful here. We're only talking about thermodynamics, so I could probably leave it at that. But really, it's the total energy that can be gained or lost in a heat exchange. The reason I say that is, again, let's say this is a block of aluminum here. I just want to be a little careful here. The atoms that make up the aluminum are then a nucleus with the electrons hooked together. To take the electrons off of the aluminum takes energy. Or when they get back, they give off energy. And so I would say this big block has energy because of the electrons hooked to the nucleus. And that's not the thermal energy we're talking about. So when I talk about the thermal energy here, I'm talking about the energy that can be gained or lost by if I put it under a flame. And if I put it under a flame, the thing I can do is make the atoms go faster, or if I cool them down, they go slower, or if I get them real hot, they break apart and they melt. But the aluminum piece doesn't come apart. The aluminum atom doesn't come apart. Or if you understand anything about nuclear physics, the protons and the neutrons can come apart and go together. And there's a lot of energy there, but that's not the energy we're talking about. We're talking about just the thermal part of it. So again, this is the total energy it has, whereas this is the exchange of energy it has. That's really what I want to focus on. Yeah.
Do they subtract the background of the universe? Or do they, how do they?
No. Because the universe, the universe has a temperature, and that would be energy that would be exchanged by heat.
Can you lower it below that? Could you gain or lose heat for something below that temperature?
Yes. If I took a piece of aluminum that was, the universe, the background is what you're saying, is about 3 degrees Kelvin. I shouldn't say degrees, 3 Kelvin. It's hard to say without Kelvin, but it's 3 Kelvin. So if I took a block of aluminum and I put it out into outer space, it would cool down to 3. But if I took a block of aluminum that was already cooled down to 2, it would warm up to 3. Yeah, so that is an exchange. Yeah, and so, no, I'm not subtracting that out. That is part of the thermal energy of the universe. Yeah, it's not high in temperature. It's big in volume, so it's a lot of energy. But it's there. It's energy that's there. Yeah.
I just don't understand how, like, turn that heat into kinetic energy?
They were already kinetic energy. Maybe I should emphasize that. If I want to get something, this cold one, hot, how do I get it hot? Okay, what am I doing by heating it? I'm getting it next to something that is hot. And so what's going on with these molecules? They're already going fast. And so I just have fast things hitting slow things. That's why they go fast. Yeah. Good. So like I said, just that question alone makes me think it's worth going to this second level. It's worth looking at the microscopic level already. Well, a couple more words here as we get started. That's the thermal energy. The next word is thermal contact. Well, hopefully that's not too surprising. If we said something is in thermal contact, what we really mean is that heat can be exchanged from each other. You see this kind of silly example here as I kind of get started into our thermodynamics is that, well, these guys, I would say, they are in thermal contact. Well, they are because their proximity. They are so close that this atom here is actually close enough that when it moves, it touches. And I would call that a physical contact. So it's not just thermal contact. The thermal contact is created from a physical contact. They are that close together that then when this one hits, it makes that one move. And in fact, the whole reason I would say the whole thing is in thermal contact is because once these fast-moving atoms slow down because they hit the slow ones here, then going back a step, these faster ones behind it will then collide into the ones that have now slowed down, making them go faster again. Only to collide with these guys, which by this time have slowed down, because now that they went fast from this first collision, they hit the guys behind them. And this whole process continues layer by layer by layer by layer back. And even though material itself does not go from one to another, none of the atoms, if this is aluminum and this is copper, none of the aluminum atoms here go over to here. Yet the energy does, right? And the heat does. Well, and in a sense, it is very much like sound waves because they're both the movement of the molecules, except the sound waves are a regular organized pattern and the heat is this random stuff. So a sound wave will go out, reflect back, and even set up a standing wave pattern of high lows, high lows, high lows. Heat would never do that. Heat would just random vibrations, hit random vibrations, hit random vibrations, and the whole thing just has random vibrations. So you get a different effect, but of course closely tied together to the molecular motion. Yeah. In fact, one of my favorite scientists, I don't know if the favorite, maybe even famous, is Richard Feynman. For those of you who might have heard of Richard Feynman. And he was great scientist, Nobel Prize, I think, in '65. But more than that, he was a really good teacher. Many great scientists aren't that great of teachers, but he was a great teacher. Anyways, he's got a lot of interviews, but one in particular asked him. Of course, this is during the Cold War of the '60s, and said, okay, if mankind blows themselves up and completely, eliminates 99.9% of the people on the population, and the world civilization ends up back into the cave time, what would be the one scientific piece of information you think would be the most important that would advance man out of this new catastrophe? You know what he said? That materials are made out of atoms that move. Does that explain sound waves? Yeah. Does it explain heat? Does it explain the transistor? Does it explain bonding of the atoms? Structure of materials? Shape of materials? Energy? And it comes down to almost everything is explained in that. And I completely agree. That is my, wholeheartedness of, I think that is it. And so, in fact, because of that, I don't know if any of you guys were around. A couple of years ago, I gave a lecture to the school on molecular motion mania, is what I call it. And I picked that topic because because it was the thing that I think would do so many different things, and I could show so many different things to a non-scientific, non-mathematical audience, and that's where I had gotten that whole idea. All right, that's all sidetracked a little here, but hopefully you get the idea. You put them together. If they can't exchange heat, we call that thermal contact. Well, if they can't, then we say they're not in thermal contact, and so one can't give energy to another one. I mean, putting something and putting insulation around it is our idea of trying to get them from not being able. It's not perfect. Styrofoam's pretty good. Fiberglass is pretty good. Putting things in outer space, that's a good example. You've got the space shuttle. Well, I guess it doesn't go in space anymore. Satellites, International Space Center. But you put them up there, and that object has an extremely difficult time of transferring its energy as all these electronics are operating on there and getting rid of that heat because there aren't any molecules around it for it to bump in and to collide into. And so we would say it is not in thermal contact with the Earth, right? And so it doesn't exchange energy with it. And so some of the things where we'll be working with, we want to know, are you in thermal contact or are you not? Well, as I said, a couple more words. The next one is what I would call thermal equilibrium. Well, you guys kind of already figured this out, but when those two objects come to the same temperature, when the molecules are moving at the same average speed between them, or maybe I should look at a more statistical level, but again, I'm worried about getting too much into the microscopic picture here. But you could imagine at some point, as these faster ones come in contact with the slower ones, and these faster ones are now slowing down, and these slower ones are now speeding up. Since it's a statistical average, even though you may say this is hot, or now they're at the same temperature, at any given instant, one of them may actually be going slow. Because as it comes along, you could have, kind of a collision where maybe this one is coming along and this one comes along and it ricochets off and this one hits just right that it actually slows down. And so you may actually have one molecule right here going kind of slow, and then it's right here and that fast one then starts it up again. So it may be going real slow, but it's only going to be for a moment because the next one's going to hit it right away. You got to remember, these hit over 100 trillion times every second. And so that would speed up, but the same thing can happen in the other direction. So as this is going, if this is equal, ones on one side are starting the ones on the other side just the same, then there's no net flow of energy. There's no net heat. And in that sense, that's what we were doing. We are now in equilibrium. We are in thermal equilibrium. The heat energy has flowed. Now there is none. And so when no heat is flowing, that's what we mean. Thermal equilibrium.
So when do we round off and say that they have reached equilibrium? They approach it, but they never, supposedly, mathematically, they never reach the same temperature.
Right. Mathematically, you're right. They do never reach the same temperature. But that's for really two reasons. One is, I'll say that the mathematics that we do oversimplify the real world. We have one perfect object transferring to one perfect object and not the rest of the world there. So they really, in the real world, they will get to the same temperature. Okay? But in our models, we get these exponential because we very easily just say, well, here I have one object with nothing else. Here I have one cold with nothing else. But then also you could say statistically they've got to come in. But then you get really probably the best thing is that's where you would get your statistical fluctuations. You would say, well, at one instant some of these molecules go a little faster, slower. And so you would never say something has the same temperature. You would say, okay, it's a little higher, a little lower. And so that's how you get to the same temperature. And as long as you're within that statistical range, you get, All right, well, those first ones I think are a little less interesting. And again, hopefully, like I said, words I think everybody's kind of heard before. Like I said, nothing too scary, and I think that's good on this first chapter, when your focus is probably on the test coming up on other material here. All right? But we'll keep going, because finally I get to the word that I'm really after here, and that is temperature. We haven't really used the word temperature yet, nor have we defined its scale, and that's where the real meat of this chapter begins. If you were saying two things are at the same temperature, isn't this what you're saying? Right? You're back here saying, well, what is same temperature? A same temperature is when two objects then are in thermal equilibrium. And so, again, kind of in this mental experiment that I had over here, we eventually got to thermal equilibrium. We started here with one thing hotter than the other. And as these molecules moved faster and then transferred over, there was heat. Energy was going. There was a net flow. In other words, more faster ones hit slower ones this way than faster ones hitting slower ones, right? And so that's why we said there was a net gain. Eventually, after a period of time, maybe a couple minutes, could be a couple of hours, but eventually we get to a thermal equilibrium. But notice on the thermal equilibrium, it's net. So, at any given instant, you could have a fast one over here hitting a slow one. And then wouldn't you say energy goes that way? But of course, a moment later, then what happens? It goes that way. So that's why we say that the net flow is zero. So maybe energy. So what are we really saying about this word temperature? Temperature then is not really its total energy of the object, is it? And I wouldn't even say temperature is the energy of one atom. What am I really saying then about temperature when I make that statement? What? Yeah, go on.
The average total energy per unit of...
Yeah. And you hit on what I want to emphasize here. Temperature then is connected then to the average energy. Temperature cannot be defined as related to the total energy in the box. Temperature is not defined as the energy of one atom, and that every atom then may be going at different speeds, and every atom then has a different temperature. That's not what we mean by temperature. Temperature is a big statistical average. It is the average energy per atom. Or, if this is a compound, I suppose I should say molecule. But that key word then is average. Because, let's go back to this Arctic Ocean I asked earlier. The Arctic Ocean here does it have a lot of energy? Well, you said yes on that one. But does it have a high temperature? Yeah, I would say no. I mean, it depends on what you mean by high temperature, of course. Okay? But as far as we're used to as normal temperatures, I would say it does not have. That's not to say it doesn't have a lot of energy. You see the connection? Why would I say the Arctic Ocean has a low temperature but a lot of energy? Answer? Yeah, the average energy of one molecule is not very much. But the total energy in is a lot. I mean, let's just compare it with a beaker of hot water. If I were to take this beaker and fill it with hot water and compare this to the Arctic Ocean and ask, which one has a higher temperature? Which one has more energy? You see the difference, right? This one, this hot water, obviously has a higher temperature than the Arctic Ocean. Because by temperature, we do not mean the total energy of that. We mean what? Per atom. And it's an average. So if I were to look at just one atom in there, it may be going really fast or really slow. A moment later, it's going to change anyways. And I would never say that's the temperature at that moment. What I would say is, statistically, over, say, a whole second, after that atom has been hit 100 trillion times, what was its average during that 1 second? That, with the average of all the other ones that are in that beaker, that is what I want to focus on. So it's a big statistical picture, and so that's what temperature is. So that's how something like this, we could say, has a higher temperature than the Arctic Ocean. But the Arctic Ocean has more energy. It's also why we could say, if we poured this into the Arctic Ocean, which way would the energy go? Would it go from the water of the beaker to the Arctic Ocean? Or would the energy go, the heat, go from the Arctic Ocean into the beaker?
With the pressure, you have the water in the beaker, have more space to expand into and put it into the...
You see, what I'm really asking here is, if I put this in thermal contact with something, if that's something like the Arctic Ocean has more energy than this, will the energy go from the high energy to the low energy? Or will it go from the high temperature to the low temperature? Do you see the difference there? It's important here we keep straight in our mind. And again, I think we can answer this on a molecular level, probably even experience. I'm sure you have taken some warm water and put it in something, or left it outside in something big like a room. The hot water cools down, doesn't it? Even though there may be more energy in the room just because there's more molecules. There may be more energy in the Arctic Ocean. But that's not the direction the heat flows. The heat flows from what? The higher temperature to the lower. Because again, how is the energy being exchanged? Back to this picture, it's based on the motion of those atoms, the ones that come in contact. And so it would be an average of the motion of those. So the issue about whether or not the energy goes from one place to another is really an issue about which has a higher average, not which one has a higher amount of energy. Did you catch that? And so I just want to make that real clear in the words here as we get started in our thermodynamics, because that could really throw you off if you don't understand, the communication that's going to take place in these next couple of chapters. Are we talking about the temperature, meaning the average energy of them? Or are we talking about the total energy of it? Which one are we talking about here? And so, as you will see real soon, and maybe more towards the end, we will get into what we call the second law of thermodynamics. It'll be very clear that the energy will flow from the high temperature to the low temperature. I can have a little tiny drop of water, and if it's at a high temperature, the energy will come from it to the rest of the world. Even though the rest of the world has a lot more energy, that little object has more temperature. And it's that temperature that comes into play. And again, hopefully you can see that by looking at the microscopic level. All right, so this brings up this whole idea of temperature. And again, like I said, this is kind of a nice chapter to get started on, because I'm sure everybody in this room had heard about temperature before they came in. What is the temperature of the high temperature for today? You may have looked at the weather report. Hopefully you didn't look at this weekend's weather report, because I shouldn't tell you, you're not going to want to do much studying if you look at this weekend's weather report. I mean, it's going to be really nice. This is beach weather. So lock yourself down in your room, close the door, turn out the lights, and study. Pretend it's raining outside here. Pretend you're on the East Coast studying all those blizzards, and you're not, out on the Santa Barbara Pier in 80-degree weather. All right. Actually, I think it was only supposed to be 77, not 80. Oh, yeah. Yeah, 80's a little hot, huh? Yeah, well. Yeah, listen to us. And you thought it was cold this morning at, was it 51 this morning? Oh, yeah. I'm sure our friends on the East Coast would really appreciate that. Montana. That's right, they could move here. They don't have to stay there. All right. Anyways, sidetrack there, but here's, yeah, you know, I was watching the news the other day, and it was bizarre. They had this, it was a weather report, and I think it was Channel 4, which couples with the Weather Channel. So they've got this reporter out there, and he's giving a live report on the beach in New Jersey, and there's snow flurries. Snow on the beach. That just didn't go well with my visual. I was like, no way. You can't have snow on the, I just kept hitting replay. No way. It's snowing on the beach. And I'm like, don't you gotta go to the mountains for snow? I just kept doing it. And the best part then is after I did that about 3 times, my wife yelled at me. We said, all right. They flashed back to the Channel 4 news from LA, and they were laughing too for the same reason. And they made a comment, and the guy on the beach says, well, yeah, well, this is not Malibu. Like, okay, well, good point here. Anyways, so our next discussion here is, of course, about temperatures. And you probably don't need me to write this on the board, but it's probably worth it. What device do we use for measuring temperature? What is a thermometer? And so, this beginning chapter is about just that. Temperature, and then the device we will use, we will call a thermometer. And so anything that can pick up really the change in temperature, which of course is connected, as we are beginning to see on a microscopic level, connected to the motion of the molecules. And so I've got a bunch of devices over here. Probably the most common device you are familiar with is this one, right? Let's take a close look at it. How does this thing work? How does it record different temperatures? And you can see why your author doesn't even bother to do a microscopic level. But I want to go the next level. How is this thing going to work? If I were to put this end into hot water, I know it's not hot, but what would happen here? Yeah, these molecules here, moving very fast if this was hot water, would do what to these molecules, which happen to be mercury in here? Make them go faster. And if they start going faster, what's going to happen?
The pressure is going to be...
Yeah, they start pushing up here. And so the height at which the mercury goes up, which right now it's at about 20, a little mark that says 21 degrees Celsius here. It goes up, up, up. And so the motion of those, and so that's how this thermometer is designed. Not all thermometers are designed the same way. This one even does the same thing. This might be a little more common, but it's the same physics. It just uses alcohol instead of the mercury. But again, if I were to put this into hot water, what would happen? It would make the molecules move faster and go up the column, right?
Any advantage of mercury thermometers over alcohol thermometers?
Oh yeah, they each have their advantages. Well, one advantage of the alcohol over the mercury is if I break it, I don't have toxic material in the ground. That's a big one. Another big one here, or the advantage of the mercury one here, is that this, when it gets really hot, doesn't turn into a vapor, explode in flames. All right, so I'm probably exaggerating. I don't think the pressure would ever get big enough to break it, but it will tear the alcohol molecules apart. So this thermometer does not work well for high temperatures. This does. The reverse is true. You get this too cold, what happens to mercury?
It freezes.
Freezes, turns into a solid. Doesn't work well at low temperatures. This does. And so the ranges are different. Yeah, so low ranges for your alcohol, high ranges for your mercury. Fortunately, both of them fit that range of 0 to 100 of what we're normally used to in a very simple lab. So we could use either one very easily, and they're about the same. Let me go.
How does a digital thermometer work?
Oh, okay, I'm glad you brought that out, because somewhere over here, I have another one. Here is a digital thermometer. Okay? Well, I should be careful. I mean, when you say digital, there is the digital part that's just displaying the numbers. Okay, that has nothing to do with actually taking the temperature, and I suppose I could build something like this and call it digital, because as the mercury goes up, I could put a camera on it. The camera could take the height of the picture, could process it, and put it on a display, and have a digital display. But I mean, I don't think that's what you were referring to. You were referring to either this or another type. This one is one we'll use a lot in the lab. It's a thermocoupler, but it has two pieces of metal touching each other. And I kind of erased my picture here, but when you put that in, I guess it looks something like this. One piece of metal, another piece of metal. They're soldered together on the tip. If you put it in something hot, that makes the atoms move. The key is the difference in material. If one material, when they move, they push and free up electrons real easy, the other material does not, then if you read the voltage between these two, then you are going to get a voltage reading and hence a temperature reading. You guys might have seen this, the reverse of this. You see a lot of these days. Well, instead of measuring the voltage to get how hot it is, it's the other way around, is you put a voltage and you get things either hot or cold. I got a little one that I like to take when I'm camping. You can plug it in the 12 volt and then it's nice cold. You can, fit a bunch of sodas in there and close it up, and it just sits on the console while you're driving, and you don't have to worry about packing ice. But it's using the electricity from the car to then get cold, as opposed to a regular refrigerator that we use Freon. Yeah.
Isn't by just using a thermometer kind of changing an experiment because you're reducing the temperature of the substance you're doing?
Right, but that's true. I don't know if you caught that, but he's saying, well, when you put the thermometer in, doesn't that affect it? Oh, absolutely, because if I wanted to know something about this, once I start putting it in here, doesn't some of the energy go into the thermometer? And so the reading I get is a little bit less. So you have to either adjust and account for that energy in your calculations, or convince yourself it is so small that it's negligible. But that's really not any different than any experiment. Any experiment we do affects what is really happening. If I have a piece of electronics and I go in with a voltmeter, that voltmeter then grabs some of the electrons that are in the circuit and pulls it out. If I have a spinning wheel and I want to know its speed, I put something on it, usually kind of rubs and spins a small wheel, but that affects the energy of that. So every experiment we make then has a consequence of it.
How do they make these precise measurements?
Well, so then you want to make sure what you are measuring with has a smaller and smaller effect. So I may go away from this to measure the temperature to this. This is small and tiny and doesn't take nearly as much energy away from it as that. So this would give me, well, other than the fact this is not built with the same quality as this one, so this would actually give me a better temperature, but this would have a less what we call thermal mass to it. And then for that reason I would get it. In the case of the example of the wheel I gave you, I would probably replace a small mechanical wheel rolling next to it with a flash photography and take a picture of it and let the computer look, here's the spoke, here's the spoke, here's the spoke. And the only way I'm affecting the wheel is by the flash of the light, and that is much less than the actual friction of a small wheel hooked next to it. Right.
You were talking about different thermometers, and I was just curious if you know how the ones where it's like a laser pointer and you point it at wherever you want to measure it and it tells you the temperature?
That is measuring, and that's more of a, not this discussion. I know it's temperature, so fair enough here. And I actually have one. I should show it to you. I'll show it to the lab or bring it next time. But it uses the infrared radiation that comes from an object. Well, actually, I take that back. I think we talked a little bit that in chapter 20. And then we also talk about it in Physics 122. But when something has temperature, okay, and again, going back to the microscopic level, if these are the atoms and they're vibrating, okay, as they vibrate, they give off what we call electromagnetic waves, which, let's see, you didn't do 122 yet, so, or did you? You did. You were there. Okay. So you remember these, right? So 122. Yeah, so that's our electromagnetic waves. They come from the motion of charged particles. Every atom is charged, and so they're going to give off this radiation. Now, it's not something you can see with your eyes. I can't look over there and say that wall's warm and that wall's cold. But I can build detectors that can do that, and that's what you're getting at. The laser beam can confuse people. The laser beam is just used so you, as the operator, know what you're pointing at. The laser beam is not any part of it. The laser beam is just helping you point at the right object. So, if this is an automobile, they'll often go in and point it at the front of the engine, the middle of the engine, and the rear of the engine and see if there's a temperature distribution or something wrong with it. One part's getting hotter versus the other. But it's not the laser that's doing anything.
So that doesn't change the temperature of the source, right?
I guess the laser slightly warms it up, but it's so small. You ever put it on your hand?
If you turn the laser off, you could still use the device, right?
Yeah, you're just not sure where you're pointing it.
And then it wouldn't affect your experiment.
Right. Except now I think you would have more uncertainty of not knowing where you're pointing than the problem of the laser beam.
Like an eyesight.
Sure. And I should add, that's no different. Maybe you've gone to the doctor and they put that one in your ear. It's exactly the same tool. They don't bother with the laser to point it because they know they got it in your ear. They just stick the end of it in your ear and click the shutter, and they open it up and they measure the radiation from it.
What do you have radiation measure?
And so they measure, yes, and I use the word radiation, but not deadly toxic radiation. Science radiation. Okay. Infrared. Yeah, infrared is a form of radiation, but not deadly radiation. Those low frequencies aren't really causing any problems that we know of. I mean, we tried to figure out. Well, your generation's actually the experiment. We'll find out with all those cell phones you're using and see how many brain cancers problems we have in 20, 30 years. But fortunately, there's been enough studies and enough time that highly unlikely, maybe a few people might have it because they were pre-exposed, but highly unlikely. Because I don't want to scare anybody, but you never know. We'll find out. Yeah. There was a time, you guys might be too young to even have had this, but there was a time that this was a big deal, and people were, I mean, there was a whole trend of you don't put your cell phone to your head anymore. Well, not back when they were so big, where you had to carry them on a cart, but back when, yeah, no, you kept them in your pocket, and you had like this microphone up here to your earpiece. Yeah. So the radiation was transmitted from your hip and not so close to your brain, and everybody was buying the new antenna and the new earpiece, and that yeah, the scare went away. All right, well, I'll keep going here. Oh, I guess I want to show you some others. I showed you kind of the most common ones, I think, to you. Ones that I'll build up in a second here is these that are on a rounded dial. These are candy thermometers here, but you can put the end in here, and the knob moves on a dial. How?
Metal?
Well, it's really the expansion again, and that's what we're going to get up to. If I take one of these apart, maybe you can see it a little better in here. This coiled up metal piece right here is going to get bigger and smaller as it gets hotter and colder, because again, the molecules are moving, right? And so if they're moving really fast, that kind of makes the metal piece a little bit bigger, and it makes it unwind. Cools down, it tightens up, right? And there's a change there. And more on that in just a second. That's kind of the next thing after we get to temperature. But I just want to say you've probably seen those. You may even have come across these, but maybe not as much. But again, a thermometer is really any device that something changes because of the motion. And when light hits objects and reflects off, what colors reflects or how it reflects depends on the arrangement of those molecules, right? So shouldn't the reflection of the light be at least a little bit connected to its temperature? And fortunately, some materials are much more sensitive to that. And so an example of this would be here. This one, if warmed with the touch of your hand, will change the molecules, and of course we change the light that reflects. So without the warmth of my hand, I think it was reflecting green. And with the warmth of my hand, the molecules have bounced a little harder and rearranged a little bit, and now it's kind of a blue, and it's quickly cooling back. The warmth of my breath turns it back to blue. This one designed to change colors between 20 and 25, so it's a good one for the room. Let's see, this one's a little high. This one says it doesn't change color until 35. That's pretty warm. I don't think the outside temperature, my internal temperature should be 37 if I'm healthy. But the outside, I don't think I'm going to change. But notice that this one has already started to change, right? It already turned green in the room, then turned blue. It would have been black if this was cold. If this was in a cold room, it would look like this one. Let's see, I'll look for, this is probably a good one. This is the 30 to 35. It changes because the room is clearly below 30 right now, and it's all black. But my surface temperature of my hand is more than the 30. And so where I touch it leaves it. And maybe you've seen, I've seen coffee mugs with this material around the outside. So you can pour the coffee in and kind of get an idea of what temperature is it in. And so when there's no coffee in it, it's black. And if it's lukewarm coffee, it's green. And if it's hot coffee, it's blue, you know, and you have a temperature. But again, maybe getting a little bit off of here, but I just wanted you to see here that there is a connection. Well, one last one. In fact, this is the one we do an experiment with. It's kind of a fun one here. This one is a pressure gauge. We often refer this to as an air thermometer, but again, any thermometer is something that would measure temperature. And how you measure temperature is just based on something changes because of the motion of those molecules. This one is a pressure gauge. And so in here I have a bunch of molecules. These molecules are then pushing on this pressure gauge, which is currently reading at 15. If I take a bucket of, in this case, ice water, and so you can kind of see the ice in there, what do you think might happen if I put it in?
Pressure goes down.
Yeah, as long as my gauge doesn't stick. And ice water is not too much colder than the room. I mean, that's only 0 degrees roughly Celsius, and the room's roughly 20 degrees Celsius. But was that enough? Could you guys see it go down? Yeah. And so now it's at about a 14. You might see it better the other direction because this coffee pot that you guys use on Fridays, I think you guys use this, right? Is about 80 degrees Celsius. And so those molecules are going, 20 to 80 is 3 times more than 20 to 0. And so I think you can see the motion the other direction a little bit better if I put it in there. See how the
talk about degrees Celsius like that multiple times, 3 times. Because you have to talk about.
No, I'm talking about the change though. Yeah, so fair enough. I'm not saying that. I'm not trying to say that the molecules go 3 times faster, which we're going to call absolute temperature here in a minute. But I'm just saying the change between room and ice is 20. The change between room and this hot water is 3 times more. So I should see more motion here, right? So again, this is what, like I said, we call an air thermometer. You might call it just a pressure gauge, but I'm using the pressure then as a way of figuring out what is the temperature. Well, here's where we need to start getting into some numbers now. Because let's actually build and have some kind of scale. Because as I pointed out here, a thermometer is a device that measures temperature. And so we just need something that changes. And so I was just trying to show you a bunch of examples. Obviously I couldn't show you everything in the world, but I could show you quite a bit. And I showed you the most common one. So I'll go back to the most common one. That we have either a mercury or an alcohol down at the bottom. And as we warm it up, those moving molecules push it up to the top. And so one of the first people to do this was Fahrenheit. So guess what we have? A Fahrenheit temperature scale. Exactly. And one improvement on that scale was done by Celsius. So we got the Celsius scale. Another improvement, and they each have their goods and bads, was done by Kelvin. So we have the Kelvin scale. And those are probably the three most common, certainly the three that we're going to carry about in this class. So let's talk about those temperature scales. Yeah.
So why does America use Fahrenheit more often than Celsius, and the Europeans often use Celsius more than Fahrenheit?
Well, I think you're really asking also, why do we use inches and not meters? Why do we use miles and not kilometers, right? And we had that system, and we never switched. Europe switched because Napoleon used it and took over all of Europe and spread the metric system. And so I guess the one thing about Napoleon conquering all of Europe was now all of Europe had a really nice base 10 system. So it was the French, probably because they also hated the English, but because they wanted to base 10, said, there's got to be a better system than 12 inches in a foot, 5,280 feet in a mile. And they came up with a base 10 system. And then they spread it to the rest of Europe, and then eventually England switched over. We tried really hard. You would be too young to remember the 70s. There was a big push to it, but there was a lot of public resistance saying, hey, when the weather report says it's going to be 77, I know it's beach weather, and I'm going to go into my basement and close the door and study for my test, right? But when the weather report says it's going to be 25 degrees Celsius, what do? Do you put on a jacket or do you put on shorts? So that's why there was a public, the point is people are used to it, and it's hard to change that. There's also just a huge cost with changing every thermometer, changing every road sign, changing the big one is changing all your manufacturing equipment. And so since the 70s, most of it has changed. You buy an American-made car, it's mostly metric now anyways. There's still some old standard bolts on them, but you're never quite sure. Yeah, and then and our resistance is probably the opposite, right? We don't want to do what the French did, right? Except finally, we actually worked together in North Africa here a couple of weeks ago. All right, but all that is to say is, like any unit system, there's multiples of them. Hopefully by the time you're done with this class, you realize that, look, it's just a different system. Convert. It's not a big deal, just as there's a multiplication factor, right? I can do energy in joules, or I can do energy in calories. I can do distance in miles, or I could do it in kilometers. All I got to do is multiply. And if it's not a multiple of 10, which is why the metric system is so nice, get your calculator out. I mean, that's the only difference, is just, can I do the multiplication in my head, or do I need a calculator? And you might be a little early to realize that, but the unit system should not throw you off. So I am not a big advocate of changing systems. I don't really care. In fact, I would even say, in a lot of sense, just the fact that you got to keep switching makes us a little smarter to figure out, it doesn't really matter on this system. It's the same energy, whether you call it joules or calories or electron volts.
If you stop watching television, all along can tell you that it sounds like every other device allows you to choose.
Fair enough.
You can use whatever you want.
Yeah. Okay, but I want to make sure I get this out here today here. So I'm going to draw a dotted line here across here, and maybe run through a little bit of work that Faraday did here. Faraday said, okay, let's set up a standard. We want to set up a standard so that as I communicate to my friends throughout Europe, when I run my experiment, I can say, I did this at, and you can repeat it. And so Fahrenheit got to thinking about this, and he said, you know what? This probably makes a lot of sense. I will use, and he did not use this immediately. He used something more along this lines, yeah?
Wait, so Faraday and Fahrenheit worked together?
No. Faraday, I guess. No, not Michael. You're thinking Michael Faraday.
Well, you just said Faraday.
Sorry. I meant Fahrenheit.
Okay.
Sorry. Yeah. Thank you. Yeah. Good question, but no, my bad. But what I want you to see here is kind of his very simple setup. It was something along these lines. You see this brass rod right here? It is about 1 meter long, although I got some hanging over the end, so I'm not going to use the whole meter. But what I do want you to see is if this brass rod were to move, can you see this dial? You see how this dial will change? It spins based on where that rod is. So I'll just move it back and forth, maybe stop right about there. I'll adjust it so the needle is pointing straight up. I'll clear off the desk here a little bit. What do you think might happen if I heat up the brass rod? Yeah. So as I heat it up, looking at the microscopic level, these molecules are going to go faster and faster and faster. And as they go faster and faster and faster, they need more space. So you can see why I like the second level, the microscopic view here. They do go faster and faster, they do need more space. And as they need more space, they kind of stretch out, and that's what we call thermal expansion. And we'll do some numbers on it in the rest of this chapter here. But did you notice the needle moved? Right? And the movement of that needle is an indication that it got bigger. And I needed that needle because I don't think it moved bigger so little, I don't think I could convince you if I just measured it with a meter stick here. But with that little needle, it has moved. And Fahrenheit realized that. He said this would be a perfect way to make a scale. What we can do is take this pipe and hook it up to some ice water. Picking ice water because he knew any of his friends, could easily reproduce ice water. And it was easily reproducible, and so he'll just run ice water through here, and we will go ahead and give a first mark right there. And call this, okay, this is ice water. Okay? In my case, I would then run the ice water through and set the dial straight up. So there's my starting point. Then that's what he did. Run the ice water straight up. And then said, okay, now if I get it warmer, the needle should move. Now what could all of my other friends do to make this repeatable? Well, they could boil water. Anybody could do that, right? They got water, they got fire, they can make water. So let's try that. So then he boils water. And of course, as you are probably noticing, if you were to make this warmer, the needle would turn. And so he sets it up so the needle turns. And he adjusts everything so the needle goes a half a circle. So it starts here, moves a half a circle. And she goes, well, I got a little protractor up there, so I've got markings for the angles. How many would fit in here in a half a circle? Yeah, so he goes, let's call this 180 degrees, yay! And unfortunately, that leaves us with some confusion today because now we got degrees for angles and degrees for temperatures. But you can see where they kind of originally come together. So he sets it up that way. He probably should have stopped there, but he doesn't. He goes, well, let's see. Can we get it colder? And he realizes, and I think you realize, how could you get it colder than ice water if there's no refrigerator or electricity? Ice water, right? Salt. You take ice water and you pour salt on it, right? Salt is that endothermic reaction. If you haven't done it there in chemistry or made any homemade ice cream, it's kind of fun. You can't freeze milk with just ice. You got to get colder than iced in order to freeze. And so if you're making some homemade ice cream, you throw in the ice and then you just pack it with salt. And that salt dissolves. It's an endothermic and it's taking energy out. It also, for that matter, melts the ice, which is kind of nice if, again, back to our friends in Montana and North Dakota and the East Coast. What do they spread all over the road when it's snowing? Salt. Why? I wouldn't say it dries it, it melts it, right. It, in the process of making it colder, turns it into a liquid, and then the liquid runs off the road, so you don't have the ice on the road there. So, and then then it gets on the bottom of your car and eats it out, and yeah, never buy a used car from, Huh? Snow. Well, okay, so if we live in Santa Barbara, getting snow might be a little challenging.
You can still freeze water sometimes out at night.
Yeah, fair enough. But if you live in Germany, you have no troubles getting snow. You live in France or England, you can get snow. Now, granted, not every day of the year, but...
On the ocean?
England gets a little bit. Granted, they're an island and they're not used to it. In fact, I think even when they do get snow, the whole place just shuts down, sort of like what would happen to us. I mean, if we got snow here, we just don't know how to handle it, you know. I don't even think near a snowplow is within 100 miles. You know, how are you going to clear the road? Just, you know. In fact, I bet if we got 1 inch of snow, they would close the schools. And the news would say, hey, they're having a snow day in Southern California. They got 1 inch of snow. Really?
Don would still be here.
That's right, Don would still be here. He'd get here somehow. Good thing for Don. He'd probably plow the road to get here for everybody else. All right. Okay, so he does try this salt water. And if you haven't tried the experiment, it's kind of fun. You know, put a thermometer in there, put a bunch of ice, put a bunch of salt, mix it around, stir it. So he does this. A lot of ice, packs it in there, and runs it through his tube. Well, guess what would happen with your dial? I guess it would go backwards, right? And so he measures. At what angle does it go backwards? And it goes backwards, 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 backwards. Guess how far it went? Good, you guys got the picture already, right? It goes back 32 degrees here, right? So he decides to call this 0 degrees Fahrenheit. So that will be our starting point. So what is ice water? Well, on this little dial, it would change by an angle of 32. So we'll call that 32 degrees. And if you warm it all the way up to boiling water, what happens? It goes up another 180 degrees from the 32. So what angle are we at? 212, right? And so that's a scale that many of you are used to, the Fahrenheit scale, where 0 is this salt, ice, water bath, 32 is just ice, water, and 212 is boiling water. And that's what most of us, I think, grew up on and used. Or maybe not so much you. Dinosaurs were still around when I was growing up, but back when you guys probably got more exposure to Celsius than I ever did. But you can see then the next level. The next level is, okay, it's an interesting scale, but it's not a base 10. And so just like the inches into feet or feet into yards or yards into miles, they're not a base 10. So let's switch this. And that was Celsius point. Celsius point was said, hey, this ice water and boiling water are great ideas. Anybody can do that. Let's use those as our markers. But as we make a mark here and a mark here, let's divide that division in a base 10 instead of a half a circle. All right? So I guess he probably had to think about, do I want to divide it into 10 pieces, 100 pieces, 1,000 pieces, 10,000, and I guess 100 seemed about right. It seemed like a good size. 10 probably was too big, and 1,000 was too many of them, and the steppings were too small. So, for what reason, I don't know, he called them 100. The part I like best is he still called them 100 degrees. Well, why would you do that? And maybe just that whole thing is set into your mindset that you got to call it degrees. But anyways, that's what he calls it. It's 100 degrees, but it has nothing to do with 100 degrees on a protractor. It's just multiple of 10. All right, so there's your 100 degrees. And better still is he said, let's use ice water and boiling water as our 0, or ice water as our 0, which makes the boiling water 100 degrees Celsius. And so again, many of you probably already know on the Celsius scale, which is what we will use. We will seldom touch the Fahrenheit one, but we will go ice water at 0, and 100 degrees is the boiling water. And so that makes a nice, convenient scale also. It also gives us the tools to be able to go mathematically from one to the other. If you know one, don't you know the other? Let's see if we can work it out. If I took this blue marker here, kind of scanned across, and say, okay, let's say this is the temperature. Whether I mark it in Fahrenheit or whether I mark it in Celsius, this is the height that the mercury goes up, right? So how would the reading over here, temperature on the Celsius scale, compare to the reading over here, temperature on the Fahrenheit scale? I mean, they're the same temperature, right? The mercury goes up the same amount. So let's take a look at it. Let's start with the temperature on the Celsius scale. Temperature, Celsius. I mean, it would be a certain number of divisions, right? But over here, wouldn't there be more divisions between ice water and the temperature? Ice water and the temperature? Would there be more here, right? Because aren't these smaller? So when you're over here saying the temperature is Celsius, you're saying how many divisions there are. This should be more. How many more? How many more would fit here compared to here? How many more here compared to here? 180. So the multiplication factor, as you guys just saw, would be 180 to 100. That's how many more marks you would have on the Fahrenheit scale. So if you take that on the Celsius and multiply by the fact that the marks are smaller, closer together, and there's more of them, you got to multiply by the factor, the proportionality factor. Unfortunately, it also has an extra offset of 32 marks. So the temperature on the Fahrenheit is not just the marks you have here, but another 32. And so, no doubt, you've seen that formula. You probably have seen it in its reduced form, because 180 over 100 is 9 over 5, 32. And so that's the mathematical connection. So if you know Celsius, you can get Fahrenheit. If you know Fahrenheit, you can get Celsius. Fair enough? And so we'll do some translations, different times, one to another. Like I said, most of the time we will really focus on these two temperature scales. These are going to be the most useful for us in a science class. But connecting it to the world around us, we'll often want to go back to Fahrenheit, and ask ourselves, is this a warm day or a cold day? Am I supposed to put on a jacket, or am I supposed to put on shorts? What is it? My son said this the other day. I shouldn't have said shorts, because I guess his teacher wore shorts. He goes, Dad, teachers should never wear shorts. And I'm all with you. I'm with you. I agree. You're not going to find me in class with shorts. But it's okay for you students, but not me. Just too old.
Is the degree symbol part of the units?
Is what?
Is the degree symbol part of the units?
Yeah. But it's not separate from the Fahrenheit, so it's degrees Fahrenheit. So, Fahrenheit cancels with Fahrenheit. Not Fahrenheit cancels with Celsius, right? And I wouldn't cancel. In other words, if I had degrees Fahrenheit divided by degrees Celsius, I would not subtract off or cancel off the degrees and just have Fahrenheit over Celsius. They're one unit. That's what I'm trying to say. Yeah. Okay, well, let me keep going here, because next comes along Kelvin, right? And Kelvin starts to think about this next level, the microscopic level I was telling you about. He starts to like I said, your author at this point has really only been talking about the macroscopic. Do you see how we could call temperature and define temperature by how much distance the mercury goes up the scale? We don't even have to know about the microscopic level. And that's what your author will do. But like I said, I think it's a little better to start that picture already. It's going to become extremely necessary and helpful as we get more advanced. All right? But Kelvin does this. He comes over here and says, all right, what I was showing you earlier was this. If this represents something cold, notice the molecules are barely moving. Hot would be this. Okay, so Kelvin's argument is more along this lines. He's saying, look, way up here at boiling water, these molecules are probably moving really fast. Something like that. And if you cool it down, it looks like that. And if you cool it again, it looks like that. And if you cool it, what eventually happens? And eventually, stop. Can you cool it more than that? No. Coming to a stop is the end of the story. And he was the first one to recognize that. He was the first one to say temperature is this average motion. And if the average motion is stopping, if all of them stop, then that is probably where we should call zero. Not ice water. And so he comes up with a scale where he calls 0 where the molecules stop. He's the first one to come up with this idea that many of you already mentioned. This is absolute 0. This is no motion.
There was an article published that they claim to have gone into negative degrees Kelvin.
For a split second, they got a gas beneath.
I wonder how they, yeah. I can't.
They said they were using a certain definition of temperature that was different than the kinetic energy.
Ah. Okay, so, and maybe I should throw something out here. I didn't really want to do it quite yet, but in 2 months I will. Okay, what Kelvin didn't know is modern physics of quantum mechanics. And what we're going to find out is that Kelvin's original definition of stopping, like you could stop a car, you can stop a bike, that does not work on the atomic level. Things cannot ever be stopped. And I think that's what you might be getting at. And so based on quantum mechanics, we come up with a new definition of absolute 0. That definition being the smallest speed it can have based on quantum mechanics. And I still don't know the answer of how they could get even slower than the slowest speed you can get unless they discovered something new. So I'm not real sure what that is saying. But they are going to start moving. We're going to revisit this in 2 months by saying our absolute 0 is going to be the slowest speed they can go.
I think the simplest explanation is probably the same as the particles they measured moving faster than the speed of light. So some sort of error on the device.
Well, that's my, I mean, that's kind of my take when I first hear it anyways. When I first hear about the faster than speed of light, it's like, oh, sure. I've heard that so many times. They're going to find something wrong. And the one you're referring to recently, yes, they eventually found a bad connection at the collider. And then that was the explanation. Yours, I don't know anything about. So you can email me the link. I'll look at it, what they're talking about. Okay, so as I said, I wanted to hopefully get that across to you then, that the idea that something cannot get colder than absolute 0. The fact that there is an absolute 0. The fact that they can not get colder is really kind of new, and only with, at least new in terms of when scientists discovered the molecular motion. They come to a stop.
How does Kelvin come up with the number?
Oh, how did he get it? I'm glad you asked, because you are going to do that experiment. It's not next week, but it's the week after that. You'll repeat his experiment. And of course, he could not get it this cold. But what he could do, and what we will do, is we will make it real hot. We will put it in boiling water and measure what's going on. We will cool it down to room temperature, measure it and see what's going down. We will then cool it to ice water, measure it, see what's happening. We will cool it one more time with dry ice and measure it. And then that's as cold as we can get in the lab. But what we can do is plot that data and see a trend line. And so extend it down until 0 motion. So we'll plot motion versus temperature. And even though we got here, we get a trend line, and we'll extend it down to get that. And that's what he did, and that's what we'll do. And at least the best we can with our equipment. Yeah. And so we'll see how close we get. Sounds like some of you know it already. Where is this 0? Where is stop? Where is no motion? Yeah, and if you're doing this on the Celsius scale, which we will in the laboratory, and what Kelvin did first is he measured this and said, okay, where is it? Here it is. And I heard you some say it. What is it? Yeah, negative 273 degrees Celsius. Really, really cold, right? It's, as I said, it's going to be 200 degrees colder than we can get with our dry ice. All right, so we're going to have to extend our line pretty far, which is why if we make a little error up here, we extend it, we get a big error down at the bottom. But it's the best we can get, yeah.
What kind of equipment do he use that we get air and we have like...
Actually, no, it's actually the same equipment. It just was better built and not abused of 20 years of students. Hey, try this. Oh, look at that. And they, so, yeah. And and didn't cost $25 to make, and it's it took a lot of care in making, as you'll see, the pressure gauge, and and it's all mechanical, so it's not, it's actually this is exactly what you will use. You will use this pressure gauge. And so really the quality comes on to how big is your dial, how much movement do you have, and how much friction do you have in the mechanical parts that move in there. And so it's amazing how accurate some of the things they did hundreds, 200s, 300 years ago, Did you see another question?
I Googled it, and it said the temperature scale moves around, and so the temperature scale simply does not hit an infinity, but jumps to negative values. So it's like hotter than infinity.
Okay, well, I'm not prepared to touch on that either, so okay. I'm not sure, what they mean there. Okay, but in the time we have left, I do want to make sure you see this, and we'll pick up the rest, after we do the test here. But this is the no motion, and it is at a low one. And so guess what we're going to call this on the Kelvin scale? 0 Kelvin.
Degrees.
No degrees. Good. I'm glad you mentioned that, right? And so Kelvin finally added that. He goes, look, Celsius should have got rid of the angle back then, but he didn't, so I will. And so we call it 0 Kelvin, not 0 degrees Kelvin. It could have been. But you already heard me today. It's hard to say that. I already said today already it was 0 degrees Kelvin. 0 Kelvin, Well, anyways, coming back to the rest of Kelvin's logic is this made a lot of sense. 100 divisions. And so Kelvin keeps that from the Celsius scale and says, look, this is that 100 divisions. It's just we're going to call 0 way down here. And mathematically that's nice because the same size of division on the Celsius is the same size on the Kelvin. So anytime we talk about a change in temperature, we won't have to specify, is it a change in Celsius or is it a change in Kelvin? Every degree change is still the same. And that's going to be very useful, we'll see. However, the absolute number is not the same. What would be the mathematical connection between temperature on the Celsius scale and temperature on the Kelvin scale? Yeah, they would just be offset by 273. So the mathematical connection is a little simpler because we don't have that prefactor in front. We don't have the different size scale. We have the same size scale, just off shifted. So we will have to ask ourselves, if the problem is asking what is the temperature, then we got to know, is this Fahrenheit scale, Celsius scale, or Kelvin scale? If the problem is what is the change in temperature, do you see how the change in temperature on Celsius is the same as Kelvin? I say that because when we have equations here, there's going to be a lot of temperatures in them, and you got to know what scale to use. Most of them, no doubt, will be Kelvin. Why? Okay, it is better. Why is it better? Right. What happens physically is related to the motion of the molecules. And so if you have equations that are related to the motion of the molecules, which means temperature on the Kelvin scale, it makes a lot more sense. So I'm hesitant to say all, but I can't think of an exception, are labeled on the Kelvin scale. Except we'll have change in temperature a lot. So when we have change in temperature, we won't care whether it is Kelvin or Celsius. You might argue that it really should be Kelvin because that has to do with the motion of the molecules. However, it would matter at that point here. And so you'll see that. But it is easy to start working on a problem and see that T in the formula and go, ooh, is this going to be a number on what scale? And so pay close attention to that. All right, well, I'll keep going. Actually, our timing's working out real well because there's just going to be a few more things left in this chapter to do after the exam, and then we can get into the next chapter that's a little more meaty, if you will. But we've kind of already started with this already. I heard you guys use the word thermal expansion. And again, it's why I said looking at the molecular level I think is very useful here, because you can see it, and you already did here. I'll show it again, but I'll start with this little demo because I just like it so much that, in effect, by the time this unit is over, you will probably get tired of seeing this machine. But it'll be here each time, I'm sure, because, as you already pointed out, if this is the molecules, say in that brass rod, or the mercury in here, and they're moving with a certain temperature, they take up a certain length, that far. And you might even say volume, but I'll just talk about length. What happens if I warm them up? Well, they move faster. And you saw right away, as they bump and hit each other harder, they expand, right? And so we saw this. It maybe is worth setting it up again real quickly and then jumping on to another one. But if I take this brass rod and I warm it up, and even though you can't visually see these little tiny molecules, as they move faster and faster and faster, as they bump harder and harder, they are expanding this rod. And sure enough, you see it move out, huh?
What's the mechanics behind the spinning wheel? How does it spin?
Oh, you want to see this crazy thing? This is the main part of it. You just put the rod on it and it rolls across the top. It spins it.
Okay, so how come if the rod doesn't roll, how come that's adding the microscopic level and makes it roll? Do you get my question? Like, the microscopic is not moving.
What's not moving?
The rod.
The rod, no, it's hot. The rod is moving. It is getting longer. It would be.
It's not only the atoms that are expanding, it's actual rod entirely.
Well, I would say the rod is the atoms.
Yeah.
Right? I mean, so I can't separate the size of the space of the atoms separate from the size of the rod. The size of the rod is from the space of the atoms. So maybe it would make sense like this. If you could imagine me pushing it with my hand, what do you see? Yeah. Right? And that's what's happening. These push on each other and push the rest of this rod forward. And so that's measuring this expansion. Okay. Those molecules are actually, the rod is actually bigger. So that's why, even without going to the microscopic level, I can just talk about this. I could say an object gets bigger. Without explaining why it gets bigger, I can just say it gets bigger. And that's the approach your author takes. I like to, as I said, go a little further, and I want you to see that microscopic level. It'll make future chapters a lot easier. It'll make this beginning chapter a little longer to discuss, but it's well worth the investment to make the rest of it a lot more understanding. Look, I'll show you some other ones. One of my favorite ones that many of you may have already seen, because we do it in 102, is just simply this one. If I take, hang on, replace Rubens tube with Fisher burner. If I take Fisher burner here and get a flame and use this sphere at the end, I'm going to get some water close by. In case I start the front row on fire again. No, just kidding. All right. But if I take this brass rod and I just aim it up for this ring, this has been manufactured so that the radius of this sphere is pretty close to the inner radius of this ring. It just barely fits. What might happen if I put it in here? Yeah. Now, on the microscopic level, I would say these molecules are going faster. And as they bump and they hit, especially the ones on the outside, move over. If we had more time, I remember doing this in a high school class, and maybe you guys did, you meet every day, and the pace is a lot slower, and you can probably breathe and sleep. But, but I remember the teacher making us all get up out of our seats and coming up to the front of the classroom, and he asked us to stand there. We're like, okay, I can stand here. Then he asked us to walk around. Okay, excuse me. So we kind of walk around. Then he asked us to run. Well, the poor students on the edge just fell over the tables here at the end. And his point was this, that what's going to happen to the molecules when they start moving faster? They're going to push, right? They're going to need more room. They're going to need more space. They're going to fall over the desk. And that's what I want you to see here. This won't fit. Cool it down. It'll fit. Okay? And so the motion, of course, does connect to the size. And I think we'll run out of time today, but there should be a mathematical connection then between the size and the temperature, right? And that's what's going to be up here, is that thermal expansion. Now let me show you this. This might catch you off guard. Let me warm it up again. See if I talked long enough. Doesn't fit, right? Let me keep it hot. Won't fit, right? What happens if I put the ring in the flame? And the real question here is, does the hole in the ring change? Does it get bigger or smaller? Oh, I hear bigger, I hear smaller, I hear same. How about that? So, watching the experiment, what's your answer? It got bigger. Smaller. Smaller. Okay? So again, I ask, if you saw it, and I think you did, does the hole get bigger or smaller? It does get bigger. We should probably draw a picture on this, because I think this is hard to see. A lot of you said it's going to get smaller, and I know why, because a lot of people do, but it does get bigger.
Why didn't it expand in every direction?
It did. All right, so let me see if I can draw a picture. All right, now, I think it might be a little easier to see if I put a square hole instead of a round hole. Now, granted, I have a round hole, so I probably am not complete here until I explain it to you with a round hole. But I think the place to start is with a square hole, even though I didn't have a square hole. So if I had a square hole and I put a flame underneath it, these molecules that make up the material would now go faster, right? And no doubt some of you, many of you, were looking at the width of this saying, it's going to get bigger. Agree. Completely agree. It would expand, and I'll put an arrowhead kind of in that direction. I would say the same thing here. It would expand that way. It would expand that way. But that's not the only thing it would do. It would expand this way. This rod is going to get longer. This rod is going to get taller. This one is going to get taller. This one is going to get longer. And so what's going to happen in this picture is it will go from here, and I'll kind of exaggerate in my picture, to this. Longer, wider rods. But the size of the hole is really defined by that. Another way of looking at it is if there was material in here, you would have no trouble saying that that got bigger if there was material in there, right? And of course you would say that because you're saying these do not push inward. But what I'm saying then is the whole thing, every part of it gets bigger in such a way that it doesn't have an internal stress. And so whether there's molecules here or not, these molecules and these molecules expand in such a way to give room for these guys to get in there. Because the reason these guys would expand is the same reason these guys would expand. And there's really molecules here. And so really the whole is defined by the circumference, if I can say circumference. I know it's not a circle. Perimeter. Circumference, right? But the size of the hole is defined by the material around the length of it, not just the width of it. So that same logic applied here. Many of you said, well, you were looking maybe at the motion of the molecules this way only. saying, look, they're going to do this, which means you're thinking these are going to go in and these are going to come out, and the width of that metal piece is going to get bigger. And that part is true. That's not changing. But in addition to that, the molecules that make up the circumference are going to, well, they're the same molecules, but the molecules will bounce left and right and up and down and forward and back. And if I exaggerate this picture, then what will happen is I will have a bigger hole because of the circumference, and also a larger width to the piece of the metal. And so I get a thermal expansion. One more real quick. What if I were to put two different pieces of metal together? One, and what I have up here, is made out of brass. The other is made out of stainless steel. And I warm them. Are they going to expand? But by different amounts, right? I mean, the molecules are going to move, but as they collide into each other, because they're different molecules and they're hooked with different forces, their collision is going to make them expand, but at different rates. So yes, both expand. But if they do it at different rates, what do you think will happen? Yeah. And as you'll see here in a minute, the brass grows more than the steel. And so there is a growing of the overall length, but there's a curving to it because one grows more than the other. And so this, yeah, and I'll run out of time today, but that's what I was showing you earlier. This is exactly how this coiled up thermometer worked either. It was what we call a bimetal strip. It's got two pieces of metal. And on this case, this is the steel, this is the brass. It's so burnt up here it's hard to tell which is which, but I'll hold it and tell you over on my right here is brass. So if I put it into the flame, what happens? And I'm hoping you can see that it does curve as it warms up. And yes, it's how it makes thermostats here. And if it cools, which we're out of time, so maybe I will encourage it to cool. Yeah, maybe I should. I just know that this beats it up so badly. It works worse and worse each time, but obviously you saw it. Go back to being straight, or pretty close to being straight. Right? Curve, straight. All right, well, we'll stop there. Remember the extra MC on Friday, the extra one on Sunday, test on Tuesday, more thermodynamics to follow.